In this tutorial, I would like to introduce you to Qiskit, which is a package in Python that is widely used for programming quantum computers. Qiskit can be used, to construct quantum circuits in many ways. You can set up your own installation of Python on your machine, or let's say you can use and use Jupyter notebook editor, and then you can also maybe use Visual Studio Code and some other editor. But for this tutorial and for this course, I would be using Google Colab, simply because you don't need a lot of installation and setup on your local computer, and you can access it from anywhere just through internet using Google Chrome. And in this session, I would just start from assuming that you never have any interaction with Qiskit before, and we will construct simple circuits and see how you can represent the input and output state of circuits on Bloch sphere, and also how you can use Aer Simulator, and how can initialize the circuit, and so on. So let's uh, get to it. And to access Google Colab, we can use the URL colab.research.google.com, and I'm using it just like you would be using it for the first time. And just so that I'm able to walk you through all the steps that are required to write circuits and execute them using Qiskit. So let's start by importing Qiskit. And in using Colab actually has only one disadvantage, and that is that usually when you set up an environment, which you can choose from here, your runtime. Let's say you can use a CPU or a GPU or a TPU, which Colab is providing for free. You have to install the packages again. So for example, to access Qiskit, we got an error. And one nice thing about Colab now is that there is an AI assistant right there that can explain to you why the error is occurring. If you click on explain error, for example, this will surely tell us that this is because we didn't install Qiskit. And it's also giving us the way to resolve this error. Okay, so now the Qiskit is installed. It's actually installing still. So let's now check by importing Qiskit if it is installed correctly. Okay, it is. Perfect. And to remove this thing, let me just press delete, so that cell is gone. Let's just check the version of the Qiskit that we are using, and it's Qiskit dot underscore underscore. There are two underscores here and two underscore on the other side of version, and I press shift enter together so to run this cell. Okay, so we are working with Qiskit version 1.3. So let's start simply and construct a simple quantum circuit. Let's see how okay, so I think this is good enough. Let's import. So from Qiskit, let me import quantum circuit. So both Q and C are with capital letters, and let's instantiate this quantum circuit class and by this, and we can specify the number of qubits in this bracket. Let's say I want to work with 2 qubit, And now I can apply different gates on these qubits by using the methods x, h, y, etc. So let's say I want to apply gate x on qubit 0. The indexing in Qiskit starts from 0. And let's say on the second qubit, I want to apply a Hadamard gate dot h on 1. And let me just draw the circuit. Perfect. So we now have a small circuit where there is an X gate on the first qubit and an H gate on the second qubit. Actually, this uh, rendering of this circuit is not very nice. We can get a very nice looking circuits if we use PyLatex ENC package. So let me install that package as well. So pip install PyLatex ENC, and once this package is installed, we can use more options to represent the circuit. Let me just delete this cell. So now I can use MPL. Perfect. So now this circuit looks much nicer than before. Okay, so we have been able to make small circuits and print them. And let's see how we can visualize the output of these circuits. So one way to do is to use a construct from Qiskit called from Qiskit import quantum info package. So there is a quantum info package in Qiskit which we can import. And let's say instead of calling it quantum info again and again, let me give it a short name QI. So I can now access this uh, package quantum info in Qiskit with just shorthand QI. Now I can use this quantum information package to find out the state vector at the output of the circuit. So let's say I call that state vector as psi1, and I can access the output of the circuit QC by the method dot state vector. And let's draw the circuit using the LaTeX form. So having installed PyLatex ENC now helps us, find the output in LaTeX form. So you see this 0, 1 plus 1, 1 is the output of this circuit. And these quantum circuits by default, they are actually initialized to state 0, 0, unless, we initialize it to a state of our choice. And we can see the initial state here. Let's say I call the initial state as size 0, and this is the state vector QC. And since I'm putting it right before these gates, so this will store the state vector right at the input. And let's say we draw both the psi 0 draw LaTeX. And actually you can't really print two outputs at the same time. You have to use a method from the display, and let's use that if you want to see both outputs at the same time. But for now, let me just put it separately. So this is the input state and this is the output state of this circuit. And if you want to print them both at the same time, let's say I call the display from IPython display library, and then let's say I have output 1 as psi0 draw and output 2 as the other output that I want, and then I can display both outputs. Hopefully, okay, this is nice. So now I can see the first output and second output, and first output is the state vector 0, which was just before these gates, and this is the state vector after these gates. Okay, so let's see how we can, in addition to the mathematical representation of the circuits, let's say if we want to represent the inputs and outputs on Bloch spheres, we can use the Bloch sphere plot, and for that, let's say I use psi0 dot draw, and I use the option Bloch. Okay, so this is this 0 0 input, because this qubit is in 0 state and this qubit is in 0 state. And suppose I want to now find out the output on the Bloch sphere. And okay, this is not gonna work out because I forgot dot draw. Okay, so you see the qubit state 0 has gone from 0 to 1 because there was an X gate, and qubit state 1 has gone from 0 to plus state. So this is the plus state because this is along an x-axis. Okay, so we can actually now go on and let's say have many qubits. Suppose I make another quantum circuit which now have 5 qubits in it, and let's say we draw its state, and I can directly ask to draw it the state instead of first storing it in a vector and then drawing it. Okay, so is there something wrong with it? Oh, I didn't tell us the state vector, what circuit to use for computing the state. Okay, so all of the qubits on 0 states, so you see they're all showing along the 0 state. And let's say now we apply various gates. Suppose I want to apply qx dot this, and suppose I want to apply a rotation gate x to qubit 1, and now I have to specify the angle of rotation. Suppose I want to rotate by 30 degree, and I have to convert the degree into radian because the Qiskit takes all angles in radian. So let's say we apply y gate to qubit 2 and ry gate to, suppose I rotate by 45 degree around y axis. Let me convert it into radian, and this is my qubit 3, and suppose qubit 5 we apply z gate. Okay, and I can either let's draw the circuit to see what's going on. So qc dot draw mpl, Okay, 1, 2, 3. Oh, so 5 is out of range. It has to be 4 because it's a 5 qubit circuit and we are starting indexing of the qubits from 0. So from 0, it has to only go until 4. Okay, all right. So this is because the circuit was applied twice. And let me run it because this is a very common error that some students do. That since I have defined the quantum circuit over here, it's initialized, and when I execute this cell, uh, each time these gates are added. So to avoid this thing, it's a good idea to have this initialization of the quantum circuit right in this box. Okay, so now doesn't matter how many time I execute, it will still produce the same circuit because it will start from this initial circuit. Anyway, to see the output of this circuit now, what we can do is now use the same command, and because now the QC circuit has all those gates, so output will have this impact. Now we can easily see that the X gate has converted qubit 0 to 1 state, and RX gate has rotated the qubit around x-axis by some angle, and Y gate has rotated around y-axis, and RY gate has rotated by an angle of 45 degree around y-axis, and Z gate hasn't done anything because the 0 state after Z gate is still 0. So this dot Bloch and this qi dot state vector, this helps us visualize the inputs and outputs of the circuits. However, sometimes we want to see the matrix that represents a quantum circuit. For example, let me start by starting a new circuit. So let's call it QC2, and it's a quantum circuit of 2 qubit. And suppose I just have a control X gate where my controlling qubit is index 0 and the other qubit is indexed 1. Let's just plot the circuit to see how the circuit look like. So this is just control X gate, and let's see what's the operator form or matrix form of this circuit. So we can easily get the operator form of the circuit by using qi dot operator, and we want to convert the QCT circuit into operator, and let me just call it QC2 operator. So this is the operator form of the circuit, and let's plot it. So QC2 operator dot draw, and suppose I tell it to draw it in LaTeX form. Now this is the matrix form of this quantum circuit, and I specifically did this example to recall this matrix from our class, where we saw that actually the matrix was not this, it was a bit different, simply because in our class we were writing this control qubit on the left side and this target qubit on the right side. And so, however, in the Qiskit, always write the Q0 qubit on the right and Q1 qubit on the left, and so on. So in qubit, in Qiskit, when we write qubits in a row, so Q0 goes all the way to the right. And if you want to reproduce the matrix from the class, we will have to change the index here so that this becomes exactly the same. So now this Q0 or this target would be written on the right, and this Q1 would be written on the left. And this is the operator form that we saw in class for this. Similarly, if you want to see for the Z gate. So this is the control Z gate, and let's say, and for the control Z gate, it doesn't matter because it's a symmetric gate. Whether control is 1 and target is 0, we'll get the same thing. Or if the control is 0 and target is 1, we will get the same matrix because it's a symmetric gate. All right, now we know how to get the operator forms of these circuits. But let's think of another scenario in which we don't want the initial state to be the default 0 0 state of the circuit, but we want the initial state to be a specific state that we want to choose ourselves, and we want to see how the circuit make the state evolve uh, the state that we have chosen. So for that, we can use an evolve method, and we can also construct our state vector ourselves, arbitrary state vector. So for example, what I can do is use numpy. So let me import numpy as np. So numpy is a package that helps us write matrices and work with matrices. So let's define a state 0 as a state vector that we define ourselves, and let's just visualize what this state vector is. So this is now a state vector that I have chosen myself, and I want to see that what happens if this state vector passes through a certain circuit. For example, let's actually define our own circuit. So suppose I have a circuit of QC3. Let me call it quantum circuit with 2 qubits, and suppose we have a Hadamard, and actually just have one thing. So let's have a control X gate like this. So this is a control X gate, and what I now want to see that how this state evolves when it passes through this circuit. So for that, let's me find the state at the output after I evolve state 0 under my circuit QC3. And let's just output the state. Okay, and you see this is what we should have gotten anyway, because this is the control qubit and this is the target qubit. Control qubit is Q0. So Q0 is on the right here. So when 0 0 state passes through the circuit, we get 0 0. And when 1 0 state passes through a circuit, since 1 is the controlling qubit Q0 and 0 is the target qubit Q1, so the control X gate is applied and we get the output state. So with this evolve method, we can actually work out the outputs for arbitrary input states. So this is a very convenient tool when we want to work out we want to work out the outputs for arbitrary inputs. And actually there's another way of doing it as well, that instead of evolving, we can initialize the circuit and then simply use the output state as well. So let me just show how. For example, so I have this QC3 circuit, and let's initialize it with size 0. Let me just draw it. Okay, so there is an error because we gave it the state, but we didn't tell it that which qubits to initialize. Okay, I didn't write the spelling correctly. Initialize, let me see. Let's check our AI assistant what we are doing wrong. So QC3 is this circuit, and it's telling us, let's just use this spelling. Okay, so no issue with spellings. Oh, the state is not normalized. No, the state, yes, this state is not normalized. This input state. So we have to divide it by square root 2. Okay, let's use this. All right, perfect. And since we had to do it before the circuit here, let's put it here. Okay, so now we have been able to initialize our circuit with an arbitrary state. And just to, show another thing, that we can also do something like this, that let's say I have QC4 and it's a quantum circuit containing 3 qubits, and I can initialize. I don't have to initialize all the qubits in it. We can only initialize a subset of those qubits as well. Initialize. Let's just copy the spellings from here. And let me draw QC4. Okay, so you see we only initialize 2 qubits, and we can do whatever we want with the qubits after the initialization. So we can initialize the circuit arbitrarily, and now and this subset doesn't even have to be continuous. We can initialize, let's say, qubit 0 and 2, even though the circuit drawing would be a little bit confusing because the third line is the middle line is somewhere under it, but it's only initializing qubit 0 and 1. Okay, and we can now check the output of this circuit. If we want to see the output corresponding to this initialization, so this is the output of the circuit for this state. So now we have been able to check the output for another state without using the evolve method because we initialize the state right there. All right, so let's now go on to one other thing quickly, and that is that we can do some of these things with the Aer Simulator as well. And for that, Let me start a new circuit and I'll call it GHZ circuit, and this is a quantum circuit of, let's say, 3 qubit, and this produces a GHZ state which actually can be obtained by, let's say, starting with the Hadamard and then applying to control axis. So let's just draw the circuit to see what the circuit looks like. So quantum circuit object is not callable, something has, let's just import again from Qiskit, import quantum circuit. Let me use the correct spelling. So we missed the CX here. Alright, so this is a circuit, and suppose I want to find out the state vector somewhere in the middle. Okay, maybe somewhere over here or here. I can put this anywhere. So what I can do, I can use GHC dot save dot state vector, and then state should have small s, actually dot save underscore, and let's check the error. GHC.save underscore state vector. It should work. We are missing from, let's actually import Qiskit Aer. So from Qiskit Aer, import Aer Simulator, and I think we will have to install Qiskit Aer for this to work. So pip install Qiskit Aer. So Qiskit Aer is a package that is used to do simulations in various ways, and it's a very efficient simulator. And in this course, and actually in Qiskit there are many other simulators available, but I'll be using only one simulator throughout this course, just to be consistent and not to confuse you, which is the Aer Simulator. So with this Aer Simulator, we can actually do a lot of other thing, and I just want to show one thing, that how to check the state vector somewhere in the middle. So once we have this, we can now simulate this circuit using Aer Simulator. So for that, I will actually have to transpile as well. So from Qiskit import transpile. So what transpile does, it transpiles the circuit for the simulator to work. And let's say we define the instant of Aer Simulator that we imported from Qiskit Aer and call it simulator Aer. Now what we can do, we can first of all compile the circuit using transpile, and let's say we call it GHZ Aer circuit. This is a new circuit. Transpile our GHZ circuit using simulator Aer. Now what this did is that it converted the GHZ circuit into the language that Qiskit Aer can understand, and now we can run Qiskit Aer, and let's say we store the result in results. So simulator Aer dot this, and then from the results we can get the state vector out and draw the state vector. Now you see, this is a state vector right over here, and we can actually put this state vector at the end to see what's the output state as well. And if you want to see the output state, so this is the state over output, and you can actually scan with it throughout. So for example, I put it right here before the circuit starts, and now the state vector should have all 3 qubits in 0,0 state. And let's say we put the state vector after just the Hadamard. Now there is a Hadamard on first qubit, which is on the rightmost side, so that has gone from 0 to 0 plus 1, and now you can see that our state is 0 0 into 0 plus 0 0 into 1. And if I want to see the output somewhere later, so wherever we want to see the state vector produced by the gates that we have inserted in the circuit, we can put the state vector there. Okay, so as a summary, I tried to introduce Qiskit and basic things that we can do with Qiskit. And this package is actually much more than that, and we'll be using it to construct quantum algorithms, and we will also be using this package to run these quantum algorithms on real quantum hardware like IBM's quantum computer by accessing them through cloud. So this is sort of one of the main package that we will be using in this course, and Aer Simulator is the main simulator that we will be using to simulate our circuits. So with this, this session comes to an end, and I hope to see you in the next session, where we will start working on some simple algorithms.